I'm going to dive into this, but before I do, I just kind of want to give you a little bit of context about what we've built. And this, so kind of, we built our own database as an alternative to kind of Spark or Storm. I'm not exactly sure what you've used, but that's kind of the context for this. We wanted a simple solution in order to effectively, efficiently, cheaply store our data, and that's what we built. As a bit of an introduction to myself, my name's Josh. I originally started out working in tech, building startups in South Africa. Worked on a billing product, worked on a website hosting company. Probably more interestingly, I guess, I worked on the core infrastructure team at Instagram, helped them build out a continuous deployment system, and helped them migrate from AWS's data center to Facebook's data center, which was a bit of an engineering challenge. Right now, I'm the CTO at Smyte, which is a trust and safety platform for the internet. Essentially, it's an anti-spam system, web and anti-fraud. Websites send us everything that's going on. We try to identify bad actors, figure out as much as we can out of the little information we have, combining counting, machine learning, and any kind of data streams we can get. This talk is really about the counting that we do. Something like how much activity is on a given IP address, which you can imagine is fairly important for spam. Like how many requests has that IP address seen in the last hour? We also look at IPv6, which has about, I don't know, hundreds of billions more addresses, which becomes very, very challenging to store. We'd look at like specific events, so how many signups has come from this single IP address in the last hour. How many signups has come from the combination of the IP address and kind of hotmail.com or gmail.com. And then also interestingly, we do this thing called a sim hash, which converts a blob of text into a very concise summary of it, I guess. And then how many actors have used similar text in the last hour. If you start seeing a lot of the same text, it probably means it's fairly spammy. This talks about this counter really, which is how many different kind of unique things has a single person used. So in this case, it's how many different unique billing zip codes has an actor used. If that number is above 3 or 4, that can be pretty bad for a payments website. Usually people only have their home and maybe work address that they use for this type of thing. The standard kind of algorithm everyone uses for this thing is called a HyperLogLog. Not going to dive into all the technical details of that. But essentially, it gives you kind of an efficient estimate count of values. So you throw a whole lot of values in, and it will tell you, I saw around 50. More importantly, what we really wanted was the sliding HyperLogLog, which is essentially exactly the same thing, but you can ask it for how many different values over the last hour, over the last day, over the last week, and it stores that way more efficiently than storing every single value, of course. What was interesting with this is when we figured out this is what we wanted and we Googled it, we got very, very little results since this thing's fairly new. This top one was actually September 2015, so that's after we built the system. And the bottom two are both the white paper explaining this algorithm. So essentially, we land up with the only available open source solution, which was this really kind of basic proof of concept written in Python. But it worked, and kind of we were just getting started with this thing, so let's take what we can, build it during takeoff, and like figure out how to get this really basic Python implementation running as one of our production databases. Just a very quick overview of what a database, like what's important for a database. This is kind of from the engineering side, but they're pretty basic concepts. Sharded kind of refers to whether you can divide your database up into lots of kind of shards. That makes it if you can't shard it, then that means you need one giant machine rather than lots of small machines. Lots of small machines is way cheaper. Accuracy is kind of, needed to actually give you the correct answers. Atomic refers to whether you can make updates in a repeatable way and whether any errors will land you up with bad data, which you never want. Cheap, durable is whether you lose your data or not. Replicated, whether you can have copies of it. So essentially, you want two different ones running with the same data at any point, so you can kind of access both. And fault tolerant is, can you still access it when one of those replicas goes down, I guess. So basically getting up and running as quick as we can. I'll just run through our initial solution, which is using this product called Redis, which is very expensive to run. It stores everything in the computer's memory, but they give you these very, very easy to use, fast in-memory data structures, and they actually also supported the HyperLogLog, which we needed. But they don't support the sliding one. But essentially, if you've got this IP address coming in, all we did was we added it to 3 different buckets, one for the month, one for the day, one for the hour, and then we could get the counts out of that. If we wanted the hour count, we just query that specific bucket. Unfortunately, the question was, are we done? We have to store everything 3 times with this solution in all of the 3 buckets. It stores it in the computer's memory, so that was super expensive for us. But we had $500,000 in cloud credit, which is kind of insane, but apparently it's what happens in Silicon Valley. We just got given all this money, and I'm like, well, we might as well use it on this since we need to get everything running. The biggest problem for us was that the buckets are not accurate. So if you're adding to an hour, you either get kind of the first half of the hour, the second half of the hour. We'd really wanted this kind of sliding count. And then kind of as a progress of what we've achieved in this database, didn't have sharding, the buckets weren't accurate. It was atomic, which is a bit of an interesting story for HyperLogLog, because you can keep adding the same data and it doesn't change anything, because you're counting uniques. Not very cheap, not very durable. Redis gave us replication, but that doesn't matter, and it wasn't fault tolerant. What we kind of migrated to from that, which is, I guess, where the kind of Spark Storm story comes in, is we added in this thing called Kafka. And Kafka, essentially, they call themselves a durable log of sequential messages. You send it any piece of data, and you know it stored it. It gives it an offset, so you can start streaming from any point in time. All your data is sitting there. We know it's sitting there. It's very, very durable. And so we just used it as a durable log of all the times we wanted to increment these counts. The other interesting thing is Kafka has a very, very smart client. So whatever, the database isn't, well, I mean, it's fairly smart, but you also need a very, very well-written client code, and they do support Python, which is fairly rare, because I think the only other ones are C++ and Java. Anyway, so all we wrote to that was the timestamp and key. So essentially, this is at 2:25 p.m., bump that count. And the initial solution was to just do exactly the same thing, move that. But then Python's pretty great with this. We could just grab this module off the internet. What we actually did as an initial solution is literally just grab the object, use Python pickle, which is a way of turning an object into just data, and save that into Redis. When we looked at that data, it kind of comes out like this. I don't know how many programming culture people are in the audience, but this looks very, very similar to a Node.js joke, which people often pull out. Python did exactly the same thing. So, but our basic solution to that was just to kind of throw compression around it, because repeated data is very easy to compress. And then you get this kind of garbage out, but it's way shorter than the original version. And we threw that into our in-memory storage. Again, are we done? Nope, this thing was still in RAM. We still had a lot of cloud credit. Unfortunately, they expire your cloud credit after an amount of time, and we were starting to reach that period in time, so we actually had to figure out the proper way of doing these things. But again, as the following summary, sharded, accurate, atomic, still not cheap. We did have durable, and we didn't have the fault tolerance we actually wanted. Because if that Redis server went down, our counts went down. And the Redis server went down quite a lot. Storing everything in memory is not very good for crashes, because you have to kind of recover everything, and it takes a lot of time. And also, Instagram also used Redis at some point in time, and they've got hours of war stories. They kind of warned me. Probably shouldn't have done that, but I also did know what I was getting myself into. But yeah, unfortunately, the cloud credit doesn't last forever, so we moved to this thing called RocksDB, which is kind of a Facebook very, very, very efficient database, very easy to use. It's best to use it with C++, but there's also a Python module which you can just basically add a database to any application very, very easily. Very scalable, very fast, very cheap. So then we started building out this kind of like version 2 of our database where we decided to try to do things properly. So for storage, we use this RocksDB. For the protocol, so we were writing our own database. This isn't that important from the data science view, but the Redis protocol is really simple, and by using the same thing, we could kind of replace Redis without actually having to change any other code. Kafka we use for durability and replication. The offset stores, so this is an interesting thing with Kafka. Because we were streaming this data in, if it crashed at any point, we would write how far we had gotten to the RocksDB database. So when it crashes, it comes back up, it knows the last place it got to, and then it can just reconsume from Kafka to catch up the last like 10, 15 minutes or whatever. And so that was working really, really well. Essentially, this would look a lot like Storm or Spark. I mean, we pretty much re-implemented it, but we had complete control over the database code, and we could write something very, very, very simple that just did what we needed. We didn't have to run Hadoop, which from the infrastructure side is a huge pain to run. And essentially, we could test this thing on a single machine very easily. But then what we could do, thanks to modern technology, is there's one more infrastructure piece we could add in, which comes from Google. It's how they kind of power their data centers. It's pretty much a Kool-Aid for making things work very, very well. Basically, it's just you can package anything you make into a container, throw it on top of Kubernetes, and it makes sure that's running. If our machines die, it moves it to another host, comes back up, starts streaming the data in again, and Kubernetes will just make sure it's always up, always running. And the other thing it can do for us is it moves the cloud disks around. So the hard drive it went down with usually is the same one it comes back up with. And so you only actually lose about 10 minutes of counts that you were running through. So you bring it back up, capture all the counts, and you're back up and running within like 10 to 15 minutes. Again, with the progress summary, so Kafka gave us the sharding. It's actually got this partition thing where every database has 20 different streams, and we hooked up a single database to each one of those streams, so we could shard very easily. The Python thing gave us the accuracy. Atomic came from the HyperLog. Now it's very, very cheap. Actually, what's interesting and very important when you're dealing with RocksDB is that it's got this thing called prefix key compression, but when we're storing hundreds of millions of counts, actually what starts costing a lot of money is the name of the counter. So we have the person's IP address in the name of the counter or their website. So how many accesses have we got from the email domain google.com? How many have we gotten from the email domain yahoo.com? And you'll end up storing the word email domain in every single counter, which is very, very expensive. RocksDB basically takes that out for you and only stores the changed bits. So you can store a lot of data in it in way, way, way less disk space. Actually, the numbers I think we got were, we moved from Redis, which was in memory very fast, to RocksDB, which is on disk, and we moved from like 500 gigabytes in memory to 30 gigabytes on disk. So cloud providers were happy, I guess, because we stopped burning as much of their credit. Still durable, which was thanks to Kafka, still replicated, and then the Kubernetes gave us the fault tolerance, which we wanted that badly. And so essentially, which I was kind of shocked when we finished doing this, was we built our own database, which sounded insane 4 or 5 years ago, but now using all these kind of off-the-shelf components, Kafka, Kubernetes, RocksDB, you can kind of hook something together, process a ton of data, and do it very, very cheaply. without that much knowledge of the core databases and all of that. So essentially, there was only kind of 125 lines when I kind of counted it of stuff that was specific to the sliding HyperLogLog. And essentially, the question we came up with then was like, what else could we do with this very, very simple data streaming database architecture? And we came up with some interesting things. So the efficient list store is the way we kind of store our labels. So as people are sending us actions, let's say it's a comment on a website or a payment, we want to label them and keep track of like hundreds of millions of labels. And so we did it exactly the same way. We piped the labels into Kafka and then into RocksDB, and then they're queryable. We built a search engine, which again was something that I didn't think we were going to do, and it seemed to work very well. Essentially there you could just trade out the kind of RocksDB part with a search engine database, still have the Python transforming the code to be searched, but it runs very well. And then the last very, very interesting one we did was accurate counters. So instead of using the sliding HyperLogLog, we traded that out for just incrementing numbers, but then we could pipe all of our data into S3 or some like more durable store, and then an hour later we would do the exact same thing but decrement the numbers. So essentially using that, we could get very, very accurate counts of how many times have we seen this IP in the last day, week, month, but pretty much to the second. And also with like a tenth of the price that cost us in Redis. Next big question is doing this, what sucked? We had a lot of pain trying to do this. Stuff you probably wouldn't experience if you were based on Storm and Spark, which is, I guess, why people do that. I don't know if you've heard of this new technology called Docker. When I was talking about containers, basically you package a program into a container and it runs everywhere. It runs the same, but it's got a lot of bugs in because it's kind of 2 years old or 3 years old. And when you're running your databases on it, those bugs really, really hurt. The Kubernetes disks, where a machine goes down and comes up somewhere else, that sometimes gets stuck, and when it gets stuck, all our counters were down. And also we recently got bit by another bug where they formatted our disks. So they essentially just erased all the data by mistake. Credit to Google, like we have some contacts there. We contacted them, told them, and they jumped on it right away. They say the bug's solved, but we haven't upgraded the version again because we kind of staying where we know it's safe, I guess. And then the future work, I guess, we don't have a solution for derived data. So data streams in and we save it in this database. Storm, Spark, all of that will let you take a further step and reprocess that data in another way. We don't really have to do that yet. We're still figuring out if we wanted to do that, how could we do that with a very, very similar setup. And we're looking at this thing called Kafka streaming, which takes a very, very similar approach to what we're doing and kind of gives you the same interface as Storm or Spark would, where you can have your script that reads through the data, transforms it, writes it back, and lands up in a database at some point in time. I guess it's probably pretty convenient that we're running late because I ran through that way too quickly. But if you guys have any questions, yeah, happy to take them. Sure. Yeah, sorry about that. Yeah, I think, I mean, on that, one of the interesting points for us was that we had to figure out a way to do this cheaply. And there are a lot of like the obvious solutions, which like when you start actually running them, I mean, so the whole Redis storing everything in memory was a bit of a joke. But Storm and Spark, What actually has landed up costing us a lot of money, which is something you never think about, but they charge you for sending data between machines, and that can land up being kind of a significant portion of your costs if you're running one of these solutions and just kind of let it do its thing and transfer data all around. So, yeah. You had a question? So, I mean, so you said Minikube, the Kubernetes thing? As far as I understand, so Minikube, as far as I understand, is just a way of running Kubernetes on kind of a single machine, which is more of kind of a development testing environment, because kind of the thing Kubernetes gives you, I didn't really dive into that, but essentially you can have 100, 200 machines, run this single piece of software, and then say, I want this data processing pipeline to run, put it anywhere, find a spot for it anywhere, and you kind of push a button and Kubernetes will find somewhere to put that. Running it on one machine is really nice for testing and development, but it probably doesn't bring you much value there. I don't know what you would actually get out of it if you're running it on. So you can run like Docker on a single machine, and it might be mostly the same thing. Yeah, so Kubernetes lets you, instead of just using one Docker, lets you run it on like 30 different Dockers on different machines. But if you're developing on one machine, you might as well just use Docker. Sure.
So you're using the last solution, RocksDB to store your counter?
Yeah.
RocksDB out of the box doesn't have any replication.
Yeah. Okay, so I didn't dive into the replication that much. So essentially, we write all our data to Kafka. So all these RocksDB boxes do is I can jump back to that slide. It's actually quite far back. There we go. So that's essentially what we write into Kafka, just the timestamp and the increment. And then we have these RocksDB servers that are now listening to that and bumping the counters. And essentially replication, instead of one server, we just set up two. They don't actually have to speak to each other at all. They both just listen to Kafka, and then you can query them for the counters. I guess so, yeah. I mean, the other kind of very interesting case is when you set up the other one, we could do it from a backup of the previous one. So we'd take a backup, create a new database, and when we brought it up, it's probably about 40 minutes since we started the whole process. It's about how long the whole backup thing takes. But because it knows it saved the position it was at in the Kafka stream, when it comes up, it will start at that position. And so they both will have the same data once it catches up. We query from both. Kubernetes has, this is kind of crazy down the technology line, but it has this magic IP thing. They call cluster IP, but essentially you get one address which links to both boxes, and it kind of chooses one at random, which makes that, and if one goes down, then it only points to the one address. So that makes it very, very easy to kind of replicate. Like we could bring up more if we had the need to. Right now we only run two because we want to still be able to serve counts when one goes down. Yeah, so we're a startup. There are 7 of us. So we don't actually have that much team structure. Caroline works with us. She's sitting at the back. But besides her, we've got 5 engineers, 1 designer, and engineers have more than enough to work on, so we kind of just sit down and work on stuff. So we don't actually have a data scientist yet. I guess the closest we have might be our teammate Julian, who's kind of the anti-spam guy. So he will sit there. So all of our kind of data, we also flow into BigQuery. I don't know if you've used that at all, but it kind of gives you a SQL interface to a ridiculous amount of data. And so he will kind of search through BigQuery, see if he can find anything interesting, bring that into our system, so we essentially write rules. So we use the way we use these counters is you write a rule saying, if we've had more than 5 purchases from the same IP address in the last hour, and the person making the purchases has used more than 3 unique zip codes, like mark this as suspicious. So he's the person that usually writes those rules. Eventually we're going to get the customers to do that. But yeah, so I guess he's sitting closest to the data. I'm on the infrastructure team, so I sit closest to this stuff and making sure the data's flowing, we're collecting everything we need to, and everything's up and running. And with me, there are 2 other people, essentially. Yeah.
Just kind of from that infrastructure perspective, like, can you speak a little bit more to how you made the decisions to choose the different technologies that you did?
Yeah, I mean,
so many options.
yeah, I can try not embarrass myself, I guess, because we didn't put that much thought into it. We put like a bunch, so there's sometimes obvious answers. We made, so Redis I'd used before, it's great, we knew it wasn't a long-term thing. Actually for these counters, we started with a database called RIAC, I don't know how to pronounce it, which was a terrible mistake. Mainly, so that database does a lot of stuff around moving data around. So it like magically will make sure your data is always available, and like, but essentially moving data from one server to another is expensive, and it treats that as just like a fact of life. And this solution, all the data is always sitting on one machine, so it's way easier to manage, way faster, way cheaper. The one other very, very nice thing that Kafka gave us was that when we started, so everything's running kind of in real time, but we could back up all the counts. So we had another thing that takes everything written to Kafka, saves it for future. Right now, we don't save everything anymore, unfortunately, but back in the early days, we could save all our data. And if we ever changed database, we could just pipe it through from day one, run through all the data again, get the latest counts in whatever database we wanted to use. Sure.
How much connection routine
So we've recently been fiddling with this. What you can do, so there's another tool called Secor, which I think was made by Pinterest. But essentially that will stream Kafka and save it to S3 or some kind of long-term storage. We were using that. We've kind of stopped because that's expensive and we've got a lot of data to deal with. So now we kind of store either 3 or 7 days worth in Kafka. Pretty much just because we only use the real-time stuff, so it's basically if something went wrong today and I only noticed it on Monday, we would still have the data to fix it. Which is why this 3-day and the 8-day is, so we can always refill a week of data. Yeah. Sure, that's probably good. Yeah, so this is kind of the, I mean, yeah, this has a lot of depth. So we definitely more on the rule-based system right now. So most kind of, so all the big anti-fraud companies, so credit card fraud, credit card laundering, all of that, they tend to use very, very heavy machine learning. And the problem with machine learning is you kind of often get this kind of single number out. So this is 80% likely to be fraud, and you don't really know why. Especially with often like spam, the numbers kind of vary a lot, and we want to know why, the customers want to know why we thought this thing was bad. So we would say, okay, this text has racial slurs in it and X amount of whatever. We're starting to combine that with machine learning, which we're only starting to do right now. I mean, we've always had a bit, but we're starting to play that a much bigger part. But that's still as part of the rule system. So a sample rule would be if this person's made more than 100 comments in the last hour and the machine learning thinks the comments are like bullying or whatever, then flag it. And so we are building up a machine learning pipeline, but I guess one of the big company philosophies is that it's not actually as important as everyone else thinks it is, which we think is a good bet, and we guess we'll see. So the rule-based system, why is that more important? Also, machine learning is great. It gives you a lot of insights that you'd probably have to work on, like kind of coming to them by hand. And when processing huge data sets, it's pretty great. The big problem kind of with anti-spam, anti-fraud, and so this is also coming from our context at like Facebook and Google and how they fight this stuff. So the game we play is always kind of this kind of attacker-defender thing with the spammers. So we have a whole group of spammers sitting in Ukraine, China. We don't really know where they are, trying to break the system. And if we have machine learning, it blocks them pretty successfully, but at some point they figure out exactly what the machine learning's learned about them and figure out how to bypass that, and suddenly we've got them on board, and the machine learning might take quite a while to pick up that and change. So we have kind of alarms set for when number of comments goes up, and this is kind of suspicious, at which point we'll go human eye, look at what's coming in, write a very, very simple rule that says, like, if this comment contains X, Y, Z, block it, and then we actually have a way of getting that into production within seconds. So can modify rules very, very quickly, get them up and running, and then start blocking the stuff before the machine learning kind of has caught up. The machine learning is very important for like figuring out whether text is bullying or whether text is this, and it's learned a whole lot of awful words, which I don't really like, yeah. Yeah, so we basically, at the moment, we take whatever we can get, which our customers tend to send us HTTP headers, kind of a bit of information about the browser. We want to get into more kind of timing, so you can kind of pick up whether it's a home user, a data center, a proxy server, so someone that's accessing through another machine. You can pick up a lot of that stuff with timing, but that requires that our customers give us that data, which is very tricky to extract. So we might at some point give them a way of doing that. So far, we just take the headers, which you can extract a lot of very useful information out of. Yeah, and lots of secrets there with just like things spammers don't know that we have to be careful about telling people, because it might land up back at the spammers and then they'll break through our system again. It really is this like long-term battle between us and them. Cool. No more questions? Thank you.